Probably the most famous experiment involving electricity, at least in the minds of American school children, is when Benjamin Franklin tied a key to the end of a kite string and sent it into the air during a lightning storm. The lightning struck the kite, traveled down the string to the key, proving that lightning is a form of electricity. Franklin also proved that objects made of metal, like the key, are good at conducting or easily passing along electricity. The story doesn't stop there, though. Franklin wasn't just outside in a storm with a kite and a key for no reason. He was looking for a way to reduce the number of fires caused by lightning. After proving that metal is a good conductor of electricity, he developed the lightning rod and placed these structures at the top of buildings to keep them safe from fire, which was probably good for the fire departments Franklin is also credited with developing. A lightning rod attracts the electric charge from lightning and conducts it by wire down the side of the house to a ground rod. This is something we in modern society somewhat take for granted, but that's because lightning rods have been installed everywhere for the very reasons Franklin were concerned about. Imagine you and some of your friends standing in a circle. Each one of you represents a single atom, the building block of all things, from apples to jet planes. Every atom has a nucleus at its center and is surrounded by a cloud of electrons. Now imagine each of you and your friends in the circle holding a single ping-pong ball representing an electron. If you were to pass the ping-pong ball's electrons around the circle, you would be replicating the flow of electricity. Electricity is when electrons move from one atom to another, in much the same way the ping-pong balls were passed from one person in the circle to another. The flow of electricity is called a current, which we measure in amperes, I, also known as amps. Conductors, like Franklin's metal lightning rods, easily carry electric currents, while insulators, like rubber, wood, or cloth, stop the flow of electricity. Besides measuring electricity's current, we also measure its voltage, watts, and resistance. The volt, V, is the power available to push electricity around a circuit. Think of it like the water pressure in a pipe. The more voltage you have, the more quickly electricity flows through a circuit. Resistance, to take the analogy further, would be pipe size and is measured in ohms, R. We measure electrical power in watts, which is obtained by multiplying amps by volts. In the 1700s, scientists got super into studying electricity. This was before light bulbs, televisions, and all the other useful applications of electricity we have now. Scientists just really wanted to understand what they could about electricity, like Franklin with his lightning experiment in 1752. Around 1710, for instance, English scientist Francis Hauksbee invented the first electrostatic generator. This created large amounts of electricity that could be used for study. Electrostatic generators also create huge sparks, which were later used in films like Frankenstein to great effect. Other scientists created instruments that could detect electricity, like the electroscope. During this time, scientists learned that electric charges could attract and repel one another, noticing positive and negative charges at work before they were identified and named. In order to make electricity useful, we had to find a way to not only generate large amounts of electricity, but to somehow store it. The battery is an early source of electricity we still use today, while large amounts of power are produced by power stations. So let's take a closer look at some of the different ways electricity is harnessed. 1. Batteries and circuits. What we think of as batteries, like the ones we use in flashlights and remote controls, are actually cells. A battery is a collection of cells, like the batteries in cars and laptops. A battery is an electrochemical source of electricity, meaning we get the electricity from a chemical reaction taking place inside the battery. The first cells consisted of two metal plates, one copper and one zinc, in a jar with liquid, usually a strong chemical that supplied the necessary ingredient for a chemical reaction to occur. The two plates were connected through a circuit, which is an unbroken wire that allowed electric current created by the chemical reaction to flow from one metal plate through the wire, through the second plate, and then finally through the liquid, also a good conductor, and back to the first plate. Even now, in order to successfully use electricity, we must have a complete circuit that allows electricity to flow in an unbroken circle. 2. Steam turbines and power stations. Soon, cells and batteries weren't enough, and we sought out larger sources of electric power. Steam turbines, developed in the 1880s, helped spur the Industrial Revolution, while inventors like Thomas Edison perfected light bulbs for use in the home. Steam turbines gave way to larger and more efficient power stations, where turbines are turned by water or by steam off of boiling water heated by burning fuels, like oil, coal, or nuclear materials. More recently, we use other energy sources that rely less on the non-renewable resources coal and oil. These other renewable sources include solar power, wind power, and geothermal power. 3. DC versus AC, the war of the currents. AC and DC don't just combine to make a great band name, they are also the different types of electric currents developed in the late 1800s. Direct current, or DC electricity, was Thomas Edison's baby, and he invested heavily in building 121 power stations across the United States that provided a direct current of electricity to its customers. DC electricity began to lose its power about a mile from the power station, though, which wasn't great for people who lived even 2 miles from a power station. Edison's rival, George Westinghouse, developed alternating current, or AC electricity. Instead of directly flowing through wire to the source like water in a hose, in alternating current electricity, the electrons rapidly alternate their direction of flow. The AC technology allowed electricity to be carried much further than a mile and maintain its power. Westinghouse won the war of the currents, and we use AC electricity today. Now that we're finished, let's take a couple of moments to review what we've learned here. Electricity is when electrons move from one atom to another. This movement of electrons is called current, which we measure in amperes, or I. For electric current to occur, there needs to be something conducting it, or easily passing along electricity, while insulators like rubber, wood, or cloth stop the flow of electricity. In terms of measurement, the volt, V, is the power available to push electricity around a circuit. Resistance is the ease with which current flows and measured in ohms, R. And watts is how we measure electrical power and is obtained by multiplying amps by volts. In terms of modern uses of electricity, we looked at the following. 1. Batteries and circuits, in which we learned that a battery is a collection of cells, and a circuit is an unbroken wire that allowed electric current. 2. Steam turbines and power stations, in which we learned about the different forms of large-scale power generation. And 3. DC versus AC, in which we learned about Thomas Edison's direct current, or DC, which is a direct flow of electricity to customers, and George Westinghouse's alternating current, or AC, which is when the electrons rapidly alternate their direction of flow. Now you should be able to explain the history and different kinds of electricity available to us today.